One of our really important uses of logarithms is solving exponential equations. Those are equations that look a little bit like this. E to the power of some function of x is equal to some number. Now, the way that this process works is if we've got e to a function of x on the left-hand side, we can take ln of both sides. And because we've got ln of e to a function, the ln and e cancel out. So we get f of x is equal to ln a. Now we may need to do some manipulation in order to get our equation into this particular form, because when we apply ln to both sides, we must apply it to the whole side of the equation, not just part of the side. Let's have a look at a couple of examples and you'll see how this works in practice. So in the first example, 2.2a, we've got 2e to the power of x squared minus 1 is equal to 7. Now this looks really hectic, but all we're trying to do is just unpack those layers around the x, okay? Think about what we're doing to that x. We're squaring it, then we're taking 1, and then the result of that, we're raising as a power of e, and then we're multiplying by 2. We're going to undo each of those steps in the reverse order. So the first thing we want to try and do is get our equation looking like this, so we can have e to a power is equal to a number. So we're just going to divide both sides by 2, right? We're going to get e to the power of x squared minus 1 is equal to 7 on 2, okay? Or 3.5 if we prefer. Next, now that we've got e to a power, we can take ln of both sides. Ln and e will cancel each other out, leaving us with x squared minus 1 is equal to ln of 7 on 2. And now we're just trying to isolate the x. We're going to add 1 to both sides. And then we're going to take the square root, not forgetting that when you take the square root of an equation, you could get positive or negative of that square root. And both of those solutions will be fine here. There's no problems having a positive or negative number in this particular spot. In example 2.2b, we have got two sides of an equation that have got e's on there, and we want to try and find a solution for x. Now this is where we come back to my favorite game in maths, which is Spot the Quadratic. It's my favorite game because they appear in all sorts of unusual places that you're not necessarily expecting. This doesn't look like a quadratic, but we can still use quadratic methods in order to solve it because it follows a particular pattern. If you look at the powers of the three terms we have go up in equivalent steps. What that means is we've actually got e to the power of 0 there. Going from e to the power of negative x to e to the power of 0 is an increase in the power of a single x. E to the 0 up to e to the power of x is increasing the power by x again. When the powers are increasing, so when you've got three terms and you've got equal distance between the powers, you've got a quadratic. So let's use those quadratic methods. Let's maybe get it into a form where it looks a bit more like a quadratic, and then let's use those same methods that we're familiar with. The sticking point here is the fact that we've got a negative power. That's really not a quadratic sort of thing. So our first step is going to be to multiply everything by e to the power of x. So we're going to get 2 times e to the power of x squared is equal to 5 times e to the power of x. All right, keep in mind e to the power of 0 is just 1, so we didn't really need it there. And then e to the power of negative x times e to the power of x is e to the power of 0, so plus 3, right? The negative x and the positive x cancel each other out at that point. Now we can get everything onto the one side of the equation. So we get 2 lots of ex squared minus 5 lots of e to the power of x minus 3 is equal to 0. We can factorize this because our numbers aren't too bad. We know we're going to have, because we've got 2 lots of e to the power of x squared, we're going to have 2e to the power of x in one bracket and e to the power of x in the other. From the minus 3, we know that we're going to have either plus 3 and negative 1, or negative 3 and positive 1. And then we just sort of fit in what we need there. So we need to get to minus 5. I reckon that's going to be minus 3 here, plus 1. Okay, 2 times negative 3 is negative 6, plus 1 is giving me that 5. If I had chosen something different, let's say I'd put negative 1 and positive 3, then using that checking method will help me figure out whether I've got it right or not. So now we go ahead and we solve our two factors here, right? If two things multiplied together are equal to 0, then either the first one is equal to 0, or the second one is equal to 0. Solving each of these, and as e to the power of x is equal to negative 1/2, or e to the power of x is equal to 3. Now, we have a small problem here. E to a power is never a negative number. So we have no solution here. But from e to the power of x is equal to 3, that means x is equal to ln 3. Okay, and that is our only solution because e to the power of x can never be equal to negative 1/2 for any value of x. In the final example here, this is a slightly more contextual one. $5,000 is invested at a rate of 5.2% per annum. If it's compounded annually, how long is it going to take to reach $20,000? You do need a little bit of prior knowledge to set this particular equation up. The final value, so the final amount, is equal to the amount that we start with multiplied by the rate of growth to the power of n, right? So how long it's taking. So putting this into context here, we're saying that we want a final value of $20,000. When we're starting at $5,000, we're increasing at a rate of 5.2%. So that growth, we'll have 1.052 times the amount at the end of 1 year, and that then is to the power of n. Now we're just solving this little equation here. So let's divide both sides by 5,000, and we get 4. We can now take so anytime we're trying to get a power as our solution, right? We're trying to work out what this power is. We're going to take the log of both sides, right? We did it over here when we had e to the power. We can do the same thing even if it isn't e. We're just going to take log of both sides. And then we can bring n out the front. Ln of 1.052 is just a number. We can divide by it. And then we can use our calculator to figure out that's about 27.3 years. And that's that process. The tricky thing, I don't want you to get really stuck on how we got this equation here into where this came from. Really focus in on going from here through to here. That's the main learning for this particular question. All right, have a go at exercise 2.2. You may need to use that formula for question 4, but it is exactly the same formula, so don't get too hung up.